Recall that throughout the year we have been applying transformations to demonstrate how parent functions can be modified or transformed to model specific applications. The trig functions are no exception. However, transformations of the trig functions have different names in many cases, and to make matters worse, the names can mean somewhat different things depending on whether we're talking to a mathematician, an engineer, a physicist, or whatever. Here's the parent function f of x equals sine of x. It is a periodic function, so it repeats at regular intervals called the period. One period is marked with the brown arrow. The period can be transformed by changing the number multiplying the x inside the parentheses. In other function transformations, we would call this number b, horizontal stretch or compression. When we deal with the sine function, this is called the wave's frequency and is often given the symbol omega, which looks like a curvy W. The period and the frequency are inversely proportional to each other, so that doubling the frequency cuts the period in half, for example. The period can be found by dividing 2 pi by the frequency, and the frequency can be found by dividing 2 pi by the period. We can stretch or compress the graph vertically, which we did in previous lessons by multiplying the function by a number a. We do that with the sine function too. However, we call this stretch or compression the amplitude, and we always give it a positive number. In other words, we know that a negative value of a not only changes the vertical height of the graph, but it reflects over the x-axis. With the sine function, we use only size and not sine to describe the vertical scale. So the amplitude is the absolute value of our transformation factor a. We can also shift the graph up or down by adding or subtracting a number we call k. This works exactly like we've seen in other function transformations. Notice that the sine function is symmetrical over the x-axis, so that when we shift up or down by k, it's like we're shifting the axis along with it. For this reason, the shifted x-axis is often called the midline and has the equation y equals k. The last of our trig transformations is the horizontal shift, often called phase shift. Phase shift also has a Greek letter symbol called phi. The definition of phase shift varies among different fields of studies, but we'll leave it to be the same as the value of horizontal shift that we have called h in the past. This is pretty much true for all definitions whenever omega, the frequency, is 1. To keep things clear, we will study functions that have omega other than 1 only when h is 0. And only a non-zero value of h when omega is equal to 1. Okay, let's see how we can sketch a transformed trig function. First, we're going to try this function here, 1.5 sine of 2 theta minus 1. So to begin with, we're going to go ahead and sketch the parent function sine of x. So if we go to our unit circle, we'll see that we have a y value of 0 when theta is 0. When theta is pi over 2, our y value is 1. At pi, the y value is 0 again. 3 pi over 2, negative 1 for y. And at 2 pi, we have 0 once more. And that completes one complete cycle, one complete period of sine of x. We'll go ahead and sketch a curve through those points. So we have just now graphed sine of theta. Okay, now let's see if we can apply the omega equals 2, frequency equals 2. This means that the new period is going to be half 1 over 2 of the original period. The frequency is twice, the period is half. So to do this, we're just going to move each of these key points halfway to the origin. So 0 halfway to 0 is still 0. Pi over 2 halfway is going to be pi over 4. Moving pi halfway gets us to pi over 2. 3 pi over 2 will move to 3 pi over 4. And that should be at negative 1. And 2 pi is going to move to 1 pi. And so now if I sketch a curve through here, I have now graphed sine of 2 pi. The frequency is twice, meaning the period is half. Pi is half of 2 pi. The next thing we can do is apply our vertical stretch of 1.5, actually our amplitude of 1.5. And so we're just going to multiply our y values by 1.5. So 0 times 1.5 is still 0. 1 times 1.5 is 1.5, and negative 1 times 1.5 is negative 1.5. So clearly we've made a vertical stretch here on the function, and now we have this function plotted. All that remains now is to subtract 1 from each point. And a good way to think about that is to just take each point and move it down by 1. So from 1.5 we move to 1/2. From 0 we move to negative 1. From negative 1.5 to negative 2.5. And from 0 again to 1. We connect the points together. And what we have there in blue then is the entire transformed function. 1.5 sine of 2 pi minus 1, of 2 theta minus 1. Now let's try graphing 1/2 cosine theta minus 3 pi over 4 plus 2. We should have a cosine parent function shifted to the right by 3 pi over 4, vertically compressed to a factor of 1/2, and then shifted up by 2 units. Let's draw the parent function first. So again, going to your unit circle for the cosine function this time, we see that when theta is equal to 0, cosine is 1. When theta is pi over 2, cosine is 0. At pi, cosine is negative 1. 3 pi over 2, cosine is 0 again. And at 2 pi, cosine is 1. And again, this completes one cycle, this time of cosine. We'll sketch our graph through here. And we've got our parent function, cosine of theta. So maybe the next thing we want to do is apply the horizontal shift. So we're going to move everything over 3 pi over 4. If you look at this scale, we have pi 1, 2, 3, 4 divisions. So each of these divisions is 1/4 of pi, or 1/4 pi. So if we're moving 3/4 pi, 3 pi over 4, we're going to be moving 3 squares. So we're going to go ahead and move this point 3 squares to the right. This point will move 3 squares to the right. This point, and this point. And so now we can just shift the graph to the right. And now we have actually graphed cosine of theta minus 3 pi over 4. Let's go ahead and apply the amplitude transformation. This time the factor of 1/2 compresses our graph vertically so that each y value is now half of what it originally was. So half of 1 is 1/2, half of 0 is 0, half of negative 1 is negative 1/2, 0 stays at 0, and again half of 1 is 1/2. We'll go ahead and sketch through here. And so now in green, we've got this part graphed. The last remaining transformation is to shift up by 2. So again, we'll take each point and shift up by 2. So starting at 1/2, we'll go to 2.5, from 0 to 2, from negative 1/2 to 1 1/2, 0 to 2, and from 1/2 to 2 1/2. Connect the points together, and now we have our entire transformed function.